Welcome to LIB Academy. In this video, I am going to take you through expectation value calculations. And we are going to prove in this video that expectation value for a stationary state is constant. What is an expectation value? Well, if you perform a series of measurements or you perform the same measurement repeatedly in a quantum system, let's say about 5 times, 7 times, the average of that experimental result is what we call the expectation value. In quantum mechanics, there are some identities that we need to know, and this is one of them. In our previous video, we proved that the probability density for a stationary state is basically the square of the wave function. The expectation value for A is written as this, equal integral from negative infinity to positive infinity. The product of the wave function, the complex conjugate of the wave function, and the operator of observable A multiplied by the wave function itself. You bring in your value element. So let me read again. Expectation value of observable A. A is the observable. And observable is what we can measure. Momentum, force, and others. But in quantum mechanics, we know that we are not dealing with the observables straightforward, but we deal with operators of the observables. So A hat here is the operator for observable A. And psi star is the complex conjugate of the wave function psi. And and this component here is the volume element. The volume element for Cartesian coordinate equal dx, dy, dz. And the volume element for spherical coordinate equal r square sine theta dr d theta and d phi. So that is what you need to know. If the wave function is in terms of x, we can just replace this term here by dx. If it is in terms of dx and dy, we can replace this term here by dx and dy. So d tau means that, detail that means that it is covering all of these. It can be a Cartesian coordinate or spherical coordinate. Sorry, psi of xt equals psi of x e to the power minus I e t slash h cross. Okay, let's proceed. The complex conjugate of the wave function indicated by psi star means the whole thing here, but in this case the exponent of e is going to be positive. If it is positive, the complex conjugate is going to take the negative part. If it is negative, the complex conjugate is going to take the positive part. In this place, in this case, the general wave function has a negative power of e. So the complex conjugate of the wave function is going to be positive I e t slash h bar. And now we bring in our operator, and then the wave function itself, which is basically going to be this term here. So psi of x e to the power minus I e t slash h bar. Then since the wave function is in terms of x here, we can just replace this, the volume element by the x. Now, we want to find a way of cancelling the exponential terms out. What we want to do here. By doing that, will it affect our operator? Lucky for us, in quantum mechanics, our operators are usually in terms of momentum and then position. Momentum P and position X or Y or T. In this case, we are free to group our exponential part and cancel them out without any problem, since our operators usually don't have time component. So let's do that. So integral from negative infinity to positive infinity, we bring psi star of x, psi star of x here, psi star of x, bring in our operator, and then psi of x. Grouping them, we should group them in such a way that the operator would be between the wave function and its complex conjugate. And then e to the power positive iet, positive iet slash h bar plus minus iet slash h bar. It is a plus, but we have minus here, so we can just write it as minus iet slash h bar dx. So simplifying this, we are going to get integral from negative infinity to positive infinity, psi star of x, a hat, psi of x, e to the power 0, because this minus that will give us 0. So e to the power 0. And e to the power 0 is the same as 1. So psi star of x, a hat, psi of x multiplied by 1, which is the same as this. So the expectation value for the observable E is simply integral from negative infinity to positive infinity, psi star of x operate, E hat psi of x dx. That is if the wave function is in terms of x. So what we've just proved here is that if you are given a wave function to operate on, you can just, to find the expectation value of a given observable, you can just write the formula straightforward as this, without including the exponential part of the function. Because when we take the complex conjugate of the wave function, the exponential part cancelled out. So if you are to find the expectation value of, let's say, an observable B, you can just write it as expectation value of observable B equal integral from negative infinity to positive infinity, the complex conjugate of the given wave function, and the operator corresponding the observable B, in this case, let's say B hat, and the wave function. If it is in terms of x, then you bring in your volume element. If it is not from negative infinity to positive infinity, if we are given other intervals, you are going to use that interval. But this is the general definition for expectation values. where B here is the observable and B hat is the operator of the observable, and psi star is the complex conjugate of the wave function psi. In this case, the volume element refers to the spatial part, the tiny area in space that the integration is taking place. If we are finding the probability of finding an electron in a space, the area covering that space is what we call the volume element. That is it for this video. See you in my next video for normalization of the wave function, expectation values of Hamiltonian operator, and the square of the Hamiltonian operator, and many more. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.